All right, so the question that's been asked of me says, among those that have been asked of me, what kind of particle interaction is most likely to occur for a substance with this formula? Well, the question is, of those categories we just talked about, which type of interparticle attraction can occur between this molecule and another one that's like it? So is this a structural, covalent, what's the word I'm looking for here? I just said it too. Gracious. Where's my... Is this a covalent network structure? How would you recognize a covalent network structure from the formula? Well, look at the examples on Table 1 on page 291. Use your tools. Quit hammering nails with your head. Oh, okay. That's not the question I asked, but I see where you're going because that was the first question I asked. The most recent question I asked was, is this a covalent network structure? You don't know. All right, look at the covalent network structure formulas. Do they have anything in common that would clue you in as to what a formula that's covalent network would look like? Huh? What? Table 1, I think it's page 291, isn't it? Okay. There's two formulas there. What do they have in common that's different from any other kind of formula you've seen that would indicate it's a covalent network structure? Subscript X. Well, what do you put in the subscript position? Huh? When you put a number in a subscript position in a chemical formula, what does it tell you? Atoms or polyatomic ions or whatever that are what? Huh? Okay, yeah, that's true in that formula, but I'm also looking at how are they put together? Why are they listed like that? What is that telling you about the way it's built? What? They're bonded together. We wouldn't have a subscript there if we weren't bonding things together in that ratio, correct? How many things are bonded together in those formulas? The covalent network structures. Wait a minute. We're talking about that little X that's different. How many are bonded together? X, what does that mean? Could be anything. Yeah. Okay, just think it through a little bit. It could be anything. It could be 10 or 10 million. All right? Does this look like that in any way? Okay, it doesn't. This is not the same. So is it likely going to be covalent network? Okay. Now, why is that X there? Remember I told you the other day, you got to think about, what does that mean? What is that X telling you? I can have as many as I want. It's going to be lots of them bonded together or a few of them bonded together, okay? This says only this number is bonded together, right? And if you remember when we're doing organic names and structures, this is an actual molecule. Remember the name of the molecule? Propane. That's an actual molecule. That's a distinct, separate molecular unit. Okay? So we're cutting out the covalent network. How about, is it metallic? No, not an atom. Not a metal. Is it ionic? No. Is it covalent? All right, so we got some covalent stuff to look at. Is it going to be nonpolar or polar covalent? And how do you know that? Good. They are actually evenly arranged. Another way to look at it is there's not a lot of electronegativity difference between carbon and hydrogen, but they also are pretty evenly arranged. All the hydrocarbons, all the simple hydrocarbons like that, are evenly arranged. And I told you that one time before. If you didn't remember it, that's fine. But, that's a nonpolar substance right there. Okay, so what forces hold nonpolar substances together? London forces, that's it. It's that uneven shift. It's that temporary shift of electrons. because they're moving around in that electron cloud. Statistically speaking, more often than not, they're sort of bunched up in one place or another, which creates a temporary polarity on the surface of that molecule, which means this then it can be attracted because that temporary polarity to another molecule of the same kind, but it's very temporary. It ain't going to last very long. Okay? To use poor grammar for emphasis. Okay?
So do we have to memorize this chart basically?
No. But you kind of got to know the way it's laid out. You need to know that nonpolar covalent has a lower boiling point.
But with the substances, do you need to know whether the substances are in that?
You need to know the rank, the five substances. Yes. There's 5 different categories of substances, aren't there? Nonpolar covalent, polar covalent.
Yeah.
Okay.
So we have to know which ones are in there?
No, you don't have to know. You should be able to know. You should be able to figure that out.
You don't know what type of substance it is?
Do you know? When you look at a formula, can you tell if it's covalent? By what? Huh? This goes back to unit 3 or 4. How do you know when you look at a formula for a substance?
If it's like metal and non-metal?
What kind of substance is that? Metal and non-metal. Ionic. Okay. Ionic is either made of metals and non-metals, or it's made of, there's a polyatomic ion in there. Okay? Covalent substances are always made of non-metals, at least for this class. Okay? Metals are always made of metals. Yeah, that's kind of hard, right? Okay. Covalent network. How do we know when we got one of those? Huh? We just said it. How do you know when you got a covalent network substance? X subscript. Because it means you got an infinite number. Small, huge, we don't know.
So basically you have to know this polar and non-polar. That's the only thing.
And we did that when we figured out polar molecules, right? There you go. And then you got to rank them together. Got to figure out where they fit. Okay? We're taking all the pieces of stuff we've learned since, well, really since the very beginning, but at least since Unit 2, and putting it all together. I told you in the beginning of this class, it's very cumulative. All this stuff builds and builds and builds and builds. Yeah?
How do you know that the
CH3, CH2, CH3.
How do you know that's evenly arranged?
Well, when we're doing molecular structures, when we're doing polar, nonpolar, and when we're talking about organic compounds, we talked about it in both contexts. Okay. If you remember, we said that methane has this shape. Remember that shape for methane? Okay. Well, if we extend that to ethane, I put a carbon here. Well, let's bring it out in front. Let's put the carbon down here. Put my hydrogen behind. It's a little easier to see what's going on if I do that. Okay. And then this is going to have 3 hydrogens. So let's see, what's the best way to do that? If you can, actually that would be, I need to put this one out in front. I have to stop and think about it myself. Okay. If you start to think about that and how it's arranged, it's a little bit hard to do it visually for a lot of people. Okay. But what I told you then was, no matter how many carbons you put in a chain, as long as it's just hydrogen carbons, it remains hydrogen surrounding everything. And it's going to end up being nonpolar. I gave you a shortcut by telling you that. Okay? Any hydrocarbon, if it's just a hydrocarbon, no other functional groups on there. That's what we spend a lot of time on, functional groups in that unit. Okay? There's no functional groups on there. That stuff, all that part of the chain is going to be nonpolar. Okay? But then we stick a functional group on there. Like this. What does that do? What is this? Is this functional group going to change things? Why? It's an alcohol. Well, how does that change the behavior? Huh? It's not an ion. What's the electronegativity difference between oxygen and hydrogen? There's a huge difference in the electronegativity between oxygen and hydrogen. It's about 1.5 electronegativity difference, which is the very top end of what we called our polar range. Remember that? That's very polar. Well, this end down here is nonpolar. So we've got a nonpolar end over here. And we got a polar end over here.
So does it make the bond stronger?
You mean like between one particle and another? Let's talk about this. Let's talk about interparticle forces and intraparticle forces. Okay? What does the word interstate mean? Between states. So if I'm talking about interparticle forces, I'm talking about the forces that attract one particle to another. That's what we're talking about here. Okay? If I'm talking about, what does intra mean? What's the difference between intra and inter? Huh? Inside. Intra means inside. Okay, there's I don't know if anybody does much. Anybody do fishing in here much? No? There's something called the Intracoastal Waterway. And what that means is along the coast, there are these islands out here. Huh? Well, there's an intercoastal waterway, but there's an intracoastal waterway. If you're talking about fishing, we care about the region between the ocean or the islands and the actual physical coast. Here we're talking about the intercoastal waterway. We're talking about how that goes between one state and the next. We can take a ship through there, so far before we're on the islands. If we want to run a boat where we don't have a lot of worry about the waves very much, a barge or something, we want to travel on the intercoastal waterway till they run out. Okay, they kind of run out around South Carolina. A lot of them around Georgia, then through South Carolina. Then you got to get out in the ocean for a while before you get back into the intercoastal waterway. Okay, but if I'm going fishing and I want to go fishing for flounder, I care about the intracoastal waterway because that's where I find the flounder. That make sense? I hope to go fishing this weekend. Intracoastal waterway. All right. Anyway, interparticle is inside the particle. What's holding the molecule together. Intraparticle is what's holding molecules together. That's the covalent bonds between the molecules. That's where we figure out the polarity of the molecule. Intraparticle force. That's what's holding the molecule together. Inside this is the structural particle for methane. The intraparticle forces in a methane are covalent bonds. Nonpolar covalent bonds. Okay? Interparticle forces is what would hold one methane molecule to another. And to use that ain't word again, it ain't much. This is a very nonpolar molecule. It's very small. And using our sort of modified Venn diagram I showed you earlier, there isn't a whole lot that holds it together. Strength of attraction between particles, not much, because there aren't a lot of electrons to shift around to cause a temporary electron density, shift in electron density. The size of the particle is small. The shape is spherical. Okay, Not much to hold it together. And unless we slow them way, way down, okay, slow them way down, we can't get that to be a liquid. It's going to be a gas. So you get to negative 250 degrees centigrade. Okay? You get the point, slow it down. Okay. All right. Interparticle forces between the particles. Intraparticle forces is inside the particle itself. Okay? All right. What was the original question now? I'll make sure I stay on the point here. Don't remember?
I think we're sitting there.
Yeah, you already answered it.
Oh, I already did? Okay. Well, what we're talking about with these kind of molecules is very little stuff holds it together, London forces. If we're talking about this molecule, what's going to hold this part of the molecule to some other molecule? Okay, what kind of interparticle force would hold this nonpolar end to some other particle? London forces. What kind of attractions could, what's the strongest attraction that this end of the molecule could hold? What? It's a dipole-dipole, but this is the strongest kind. This is the strongest kind. This is going to be where you have hydrogen bonding. Anytime you have nitrogen, oxygen, or fluorine bonded to a hydrogen, the potential for hydrogen bonding occurs. And if you remember, that's the strongest kind of what we call the polar forces, the dipole-dipole forces, even though I said that there's really the latest research says it's not, it sort of spills over a little bit beyond dipole-dipole into a sort of covalent bond too. Okay? So anytime OH is there, well there's O and there's H, I've got the potential for dipole-dipole attractions. That's a pretty strong interparticle force, at least in the polar area. It's a very strong polar attraction. That's what we're going to call it anyway. Okay? Now, in terms of ranking these, the strongest hydrogen bonding can occur with an HF group. So this is, we're talking about hydrogen bonding here. HF to HF groupings. Okay? Well, fluorine already has 7 electrons. Oh, now we're going back how far? Unit 3? Hydrogen has 1 electron. I can only bond 1 hydrogen to 1 fluorine. It's done. That's it. Nothing else can bond here, right? Hydrogen fluoride's done, finished. You can't attach it to anything. So that doesn't help us a whole lot because it's its own thing. All right? Then in the middle, then, is OH groupings. So any attraction between OH and OH, that's not as strong as HF, but this is the one that affects all these kind of structures, isn't it? Any of these hydrocarbons that have OH on the ends, alcohol groups on the ends, this is where we start to get some strong attractions. Okay? But the weakest of the 3 elements that can bond to hydrogen and then have hydrogen bonding to another group like that is NH2 to another NH2 grouping.
And when it's stronger, it has a higher boiling point?
Yes, because it's held together, hard to get it apart to be a gas. Oh, they can't see it on camera. Hard to pull it apart to be a gas. Okay, what? Oh, hard to pull it apart and let it be a gas. Okay.
It has a higher boiling point and melting point? Or
Higher boiling point, higher melting point than other, say, polar molecules or even the nonpolar molecules.
okay.
Okay? When you get into these stickier, all right? They're hard to pull apart.
And then lower freezing point, or is it a higher freezing point?
Well, freezing point is trying to go in the other direction. The freezing and melting point is the same point of temperature. It's all about removing energy or putting energy in, but hold on to that thought because that question really doesn't come up till Unit 10, okay? Just know that it's the same temperature. If you pull energy out at that temperature it freezes, you put energy in at that temperature it melts. Okay, for right now that's about the only thing you need to know about it. It kind of confuses students, but we'll get to it when we get to it, all right? So, and I think we did this already. We said if I have a CH3, CH2, CH2, CH3, let's see, what is that? Methylpropane. All right, CH3, okay? What's going to hold a butane to another butane? Two possible answers. Huh? Where's the nitrogen, oxygen, or fluorine here? It ain't there. Okay? These CH3, CH2, those hydrocarbon groupings are what? So this is nonpolar. What's going to hold one nonpolar molecule to another? London forces. The sort of frivolous answer is not much. Okay? Not much is going to hold it together. Because London forces are so weak. Not much. Okay? Alright. Nah, not really. Can't put it on the test. Alright, but what if I replace this group over here with an OH group? You got more to hold it together. Which one of these is going to have the higher boiling temperature? The bottom one, because there's more holding together. Hard to pull it apart. Right? Harder to pull it apart. Isn't it that hard? It's kind of like Velcro. Alright? I mean, you could think about it like that if you want to. Some Velcro is better than others, right? Okay. Well, so remember, NH2 groupings are the weakest of the hydrogen bonding. So if I have this kind of molecule and this is all that's together in this substance, okay, a bunch of these molecules. Which one of these two has the higher boiling temperature? The OH group, because it's holding together stronger than this one is. Okay? What if I had, let's see, this. Of these two, which one has the higher boiling temperature? One on the right, because there's even more hydrogen bonding because it's got two of those groups, and this is the stuff that keeps your car from boiling over. Ethylene glycol, antifreeze. Also keeps it from freezing in the winter. Ethylene glycol. Ethylene glycol.
Are you going to ask us the stuff or liquid or gas?
Well, relatively speaking, I could. Okay? Now, there are 3 examples in your handout to help you figure some of that. Actually, 6 examples in your handout to help you sort of figure that out. You've got to extend the thought process. Let's look at this table on... Well, we can use this one on page 293. Table 3. Let's see. Of these drawings here, which one might give you a clue about whether this right here is a solid, liquid, or gas? The first 3 got OH groups on it, right? The difference is these only have one OH group on it, and this one has 2. Okay? All right. Now, you got to remember, though, we've got this nonpolar section in the middle. Okay? There's some other structural stuff that I'm not going to get into right now, but this kind of nonpolar stuff in the middle, some polar stuff on the end. These are all tending to be liquids at room temperature pressure. Let's look at the boiling temperature. Okay? For the really small one, has a low boiling temperature. A slightly larger, higher boiling temperature, slightly larger than that, an even higher boiling temperature. So what it means is the longer this chain gets, the more that the London forces are coming into effect, in addition to the OH groups, the hydrogen bonding groups. Okay? So hydrogen bonding keeps all these things a liquid. These OH hydrogen bonding keeps all these a liquid. And the longer my hydrocarbon tail, I'm going to call it, is, the more it tends to hold it together even more, making the boiling temperature go even higher, harder and harder to pull it apart. Okay? All right, let's look at this then. Got a lot of stuff to hold it together, right? It's going to have, you think, a higher boiling temperature or a lower boiling temperature than these? Higher boiling temperature than those? Okay, that's good. Is it, so it's probably going to be what at room temperature and pressure then? Liquid. Okay? You could say solid. You could argue for that. And just given that question, I wouldn't argue about it one way or the other. I give you, probably some credit for it, but the best answer is probably liquid, because I don't give you any examples of hydrocarbons with other groupings on there that are going to be solids, except for that. Now we get the really long hydrocarbons, like carbons that have hydrocarbons with 15 carbons in a row. Then we start getting stuff like the stuff you put on the highway, blacktop, okay, tar. Then it starts to be a solid. But we're not going to work with really, really long things like that for the most part. Okay? Yes? I might ask you what the forces are. I might ask you what physical state is going to be in. Because I think you have enough information to make a reasonable judgment about that. Some are. Huh? Say that again? Can't hear you for the noise in the hallway. Sure. There are two kinds of forces involved in keeping this. The interparticle forces, there are two kinds involved right here. What are they? Two kinds of interparticle forces.
Isn't there London for the nonpolar one?
Sure, that's the London forces here. Right here. Here's the London force stuff. Dipole, dipole. In fact, this even goes beyond simple dipole, dipole into hydrogen bonding. Hydrogen bonding is the strongest of the dipole, dipole forces. Remember that? Can you remember that part? Okay. Hydrogen bonding is the strongest of the NOF. Or maybe you like FON. Or phone. I don't know. If I have nitrogen, oxygen, or fluorine bonded to hydrogen in some structure, I have the potential for hydrogen bonding. That's the only time you can have it. Those three. Say what? Oh. Okay. Yep.
How would you be able to tell if it was gas or gas? Because on the target side, if it doesn't make bonding with hydrogen, it would be gas.
Okay, well, the NH2 grouping, remember, is not as strong a hydrogen bonding grouping as the oxygen is. Okay? So this is just an example showing you that if it's really small, then there's hydrogen bonding going on, but at room temperature pressure, not quite enough to make it pull together into a liquid. Okay? And for this one either. But then when we get up to a longer hydrocarbon tail here, there's enough additional London forces to pull it together into the liquid state. So we're combining the hydrogen bonding that's occurring between one NH2 group and another with the London force stuff that pulls it together. Remember I did some drawings the other day where I showed you how the electrons can have that temporary shift? Oh, I'm sorry. Yeah, and I have not been able to get it to upload into YouTube yet. I'm sorry. It's right here on my computer, but I can't get it to upload just yet. I don't know why, but it's not yet done. So, yep, I'll try my best to have it done for you. What?
So if there's more than 4 on the carbon chain, it's a liquid?
It's not. There's not one single magic number. It just happens to look like it's magic for this NH2 grouping stuff. Okay. There's all kinds of things that go in there. What I'm looking for you to do is to make a reasonable judgment and be able to justify that claim. If you can do that, you should be able to answer all the questions adequately.
Okay, I have another question. You just asked what two forces were holding that chain together with the alcohol.
Yep.
It was London and yellow.
Dipole, dipole. Please don't pronounce it dipole. I have students some years that just can't seem to get dipole down. I know I have a terrible time with names, okay, so I don't have any room to be blaming anybody for anything, but it's dipole, okay?
Will you ask us for what force will be between each of molecules?
Yeah, sure. Be specific then. You gave me a general question. Be specific with a question. I'll give you an answer.
But if you have two of those molecules, how would they bond together?
They're not going to bond together. Well, you could call it bonding and hydrogen bonding, okay? Because remember that's somewhere between covalent bonding and dipole forces holding it together, okay? Dipole attractions. But there are two kinds of forces affecting the attraction of this molecule to another one like it. On the ends of the OH groups, which have a very strong hydrogen bonding and therefore a dipole force to pull it to the next molecule. And in the middle is the hydrocarbon grouping, which is nonpolar, so the force that's involved here to attract this molecule to another one would be London forces. We have a temporary shift in electron density, creating a temporary, let's see, what's the word I'm looking for? Shift in electron, temporary polarity. That's what I was looking for. Okay? Yes? Would I do number 27? Okay. I'm not sure if I have enough time, but I can at least start it. Okay? Let me stop